So, what we've been doing here in both this example and this example is we've been factorising the numerator in here. So what I want to do now is just go through and give you, you can see that it's handy to be able to factorise expressions, and later on when we come to solve equation we'll also find it to be useful. So we need to get better at this factorisation process. So let me just go back and make sure that we've done it thoroughly. So let's first of all make sure that we know what we're doing. So here, writing an expression, so writing an expression as the product of sub-expressions is called factorising. Now, this sort of thing probably isn't foreign to you, I don't think, because once again, remember, algebra is just following arithmetic, and if I had 24, if I asked you to factorise that, you could say, look, I could write that as 6 times 4. Right? I've written that as the product of two smaller numbers. That's called factorising numbers. We're doing the same thing here as we're factorising expressions. We're writing the expression as a product of two or more sub-expressions. Now, factorisations aren't necessarily unique, because I could also write this as 8 times 3. Doesn't have to be just 2 either. For example, in here I could write this as 3 times 2 times 4, and so forth. And in fact, I could actually use a whole lot of, I could go index notation, and I could write it as 2 cubed times 3. They're all different ways of writing down a factorisation of 24. So in here, when we have an expression, we're going to try and write it as the product of 2 or more expressions. The answer may or may not be unique, in fact. And as I tried to explain, over there, factorising is usually based, or quite often based, on the distributive law. It says, so I've highlighted again, it says if I have 2 terms and I see A in both of them, then the distributive law says I can write it round as A times B plus C. All right? So every time we factorise, we are using the distributive law. Remember on Tuesday, every time we expanded brackets, we were using the distributive law. So expanding is using the distributive law one way, factorising is using the distributive law back the other way. Okay, so expanding and factorising are just inverse operations, if you like. One undoes the other. So, we are going to see a number of ways of factorising. The first one is to do what we were doing over there before. We look for a common factor in all of the terms. That's what we did over here. We looked for a common factor in every term there to factorise it. So that's always the first thing we try to do. So here in part A, it says 2x on 3 plus 4 on 3. Is there something that's common to both of those? Now, it may or may not be obvious, but it looks like 2/3 is common to those. So if I put 2/3 out the front, what have I got to multiply 2/3 by to get x? 2x on 3, I should say. I guess, look, if I wrote that as x on 1, it would be obvious, wouldn't it? Because that's 2 times x, 3 times 1. So x on 1, of course, x on 1 is just x. Plus, here I would put 2 on 1. 2 times 2 is 4, 3 times 1 is 3. And so I can write that as 2/3 x plus 2. This one's a bit simpler. What can I see that is common to every term? I can see a 2 and I can see an x. So sitting here I have 2x. Then I think to myself, what have I got to multiply 2x by to get 2x cubed? And I see x squared using my laws of indices. And what have I got to multiply 2x by to get 4x? 2. And as you can see, I've written this as the product of two sub-expressions. So that is a factorisation of the left-hand side. C 2x squared plus 4x cubed. Now, I could write this in a lot of different ways. I can see 2 is common to everything, so I could write that as 2, and then that would be x squared plus 2x cubed. That's certainly a factorisation. However, I can see in here there's also an x is common, so I could write that as 2x. Now I'd have to multiply that by x plus x, 2x squared. 2x times 2x squared gives me 4x cubed. That's another factorisation. And I can go even further. I could actually say 2x squared is common, and then I would have 1 plus 2x there. They are all possible factorisations. This last one, we would say we've factorised fully, because in none of the expressions can I go any further by finding any common factors. So this one is fully factorised, sitting there, where I found the largest common factor of all the terms. And lastly, in D, 6ab plus 8ab cubed c minus 2a squared. So what can I see that is common to all terms there? I can certainly see a 2, I can see an a. I can't see a squared because there's only a's there. So it looks like 2a is as big as I can get. So let's take 2a out. What have I got to multiply 2a by to get 6ab? So I'll clearly want a 3. That gives me 6a, and I'll want a b in there. So that'll give me 6ab. That's that one. Now I come to the next term. 2 times 4 gives me 8. I've already got the a, so I'll need b cubed c. And lastly, what have I got to multiply 2a by to get minus 2a squared? And I guess the answer is minus a. And there is that expression factorised. Okay, so in this example, we tried to factorise the expression by looking for a factor that was common in every single term. We can factorise expressions sometimes even when this is not the case. And in these examples here, it says factorise the expression. What we're going to do is we're going to look for a common factor just in some of the expressions and see what happens in here. So, for example, so I'll say here, by looking for common factors in just some of the terms. So if I was actually asked to factorise an expression, the first thing I would do, I would look to see, is there a common factor across all the expressions? And in here there's nothing common to all 4 terms there. So I can't use that technique. So I can't use what we did in example 1 over there, in the previous example. So my next thing that I would try, after trying the first thing, is look for some common factors in just some of the terms. So let's go here. In A, I've got AB plus 9A plus BC plus 9C. Now in the first 2 terms, I can see A is common. So I'm going to take that out. So I'll go A, and that will leave me with B plus 9. So that was from those 2 terms. Now look at the remaining 2 terms, and I see C is common. So I'll go take C out and I'll have B plus 9. And now I have a common term in here. And so I can take that out. And so this becomes B plus 9, and here I have A plus C. B plus 9 times A gives me the first term, B plus 9 times C gives me the second term. And there is now my expression factorised, even though we didn't have a common factor across all 4 terms. Does this always work? Not very often, but sometimes it does. It's just one of those things that you look for. Let's try B. So, first 2 terms have an M in common. And that leaves me with an M minus N. The next 2 terms have a 6 in common, and I'm actually going to write this as minus 6 so that I actually get plus M in there, because minus 6 times M is minus 6M. Now to get plus 6M, I have to write minus N there, because minus 6 times minus N gives me plus 6N. So can I highlight that and say, look, that plus comes from that minus and that minus. That's something to be wary of when you're trying to do these things. But the beauty of all of this is that M minus N is now common. And so I can write this as M minus N times M minus 6. And there is my left-hand expression factorised, written as the product of 2 smaller expressions. So now let's try and do C. First 2 terms, I'll take x squared as common, and I'm left with 5 minus y. And in here I can see 3, I think, is going to work, and I want to be plus 5, so I'm going to take out minus 3. And that now, minus 3 times 5 gives me minus 15. Minus 3 times minus y gives me plus 3y. And that's nice because my 5y is now common. So 5 minus y, x squared minus 3.